So in this video, we're going to talk about stereochemistry and reactions, and what that means is how pre-existing stereo centers affect the outcome of a reaction. All right. So real quick, what we're going to learn is what a racemic mixture is. We're also going to learn what happens in a reaction if there's a stereo center present in one of the reactants. What effect does proximity play of the pre-existing stereo center, and how that pre-existing stereo center affects the outcome of the reaction, and what happens when you mix something that's chiral with something that's achiral. Remember, achiral means no chirality, right? And chiral means something that contains at least one chiral center. So here's a reaction that you should have learned in part one of organic. It's electrophilic addition. Remember, you add take a double bond and add HX, X being a halogen. And then if you remember, this happens by Markovnikov addition, meaning that the bromine adds to the most substituted carbon, and then the H adds to the least substituted carbon. So over here, these are your two products. Don't really want to get into the reaction per se, but I really want you to look at the two products. Notice this stereo center here is R, and this one is S. All right, very important. Notice the ratio: 50% R, 50% S. All right, both of them are formed in equal amounts, so we call that a racemic mixture. All right, so a racemic mixture is an equal mixture of stereoisomers in the product. Now, if there's more than one stereo center, then obviously it's not just going to be simply R or S, because they're going to be either enantiomers or diastereomers. But in this case, you get an equal mixture of enantiomers. One of them is R, one is S, and both present in 50%. All right. Now let's look at the mechanism. Hopefully you remember this mechanism well. All right. If you'll notice, here's the double bond attacking HX. Here's the bond between HX breaking and the electrons going on the bromine. You get a carbocation intermediate. And so the reason why you see this 50-50 mixture is because that carbocation intermediate, that carbon, uh, has an empty p orbital, and so the bromine that you lose here can now attack from here or from here without any restriction, right? And so that's how you're able to get the two products in equal amounts, the S and as well as the R. All right. In general, if you mix something that's achiral with something that's achiral, both of these are achiral, neither one of them has a chiral center, you get a racemic mixture. That means, again, 50% R and 50% S, or an equal mixture of enantiomers. All right. If you think about this in terms of 3D, this is a 3D depiction of the carbocation intermediate. Let's put the orbitals in. And so now you see that this is bromine. Bromine has equal access to the top as well as the bottom lobe of that p orbital. And so because of that, right, there's no restriction for how bromine can add. It can add either side with the same amount of energy. It does not cost any extra energy to go through this pathway or through this pathway. So you get an equal mixture of R and S. All right, now let's think about this in terms of the same molecule, but now with a pre-existing stereo center. So here's a stereo center here. This methyl group, it's set and it's adjacent to the reactive site. And so with this reaction, what we notice is something different. Now the ratio of products changes. All right. Now you have um, two products, and one is minor, one is major. This one is formed in 30%. This one is 70%. All right. Big difference from before when it was 50-50. All right. So let's think about this, and let's look at the reaction mechanism. We see again, same mechanism. You get the carbocation intermediate here, and notice the pathway here to get to that top lobe is blocked because of the CH3, and the pathway here is not blocked. So the minor product is going to come from here because it costs more energy for this bromine to come from this side. The major product is going to come from here because it costs less energy to come from this way, right? So from this pathway, you're going to get your minor product, and then this pathway is going to give you your major product. Keep in mind, like we said before, something achiral plus achiral is racemic. If you mix a chiral reagent with an achiral reagent, you're going to get uh, an unequal mixture of stereoisomers. So in this case, it was 30 to 70, right? Before it was 50-50. Now let's look at this in terms of what happens. So the pre-existing stereo center, the methyl group that was there, okay, that restricts approach, right? And so here I have here like a little screen. So when bromine is trying to come in from this direction, let's watch what happens. Bromine basically gets kicked back out because the methyl group here is blocking the approach. So let's look at it again. Bromine is trying to come in, it gets kicked back out. So the methyl group restricts the approach from the top, forces bromine to come in from this way, and so now you get a unequal mixture because it costs more energy to come uh, from this direction up top. Let's look at it again. All right. So what we know about a pre-existing stereo center is this: it's going to dictate the product distribution. It's going to tell you how much R or how much S you get, right? And also the products that you do get, they won't be racemic, so it won't be an equal mixture of R and S. Now it'll be an unequal mixture, and that ratio is going to depend on how close that chiral center is to the reactive site, as well as how big it is. All right. So when you look at this, think of this in terms of baseball. All right. So the pre-existing chiral center is like a baseball bat, and so when the reactant tries to come in, the baseball bat hits it and knocks it out. All right. Let's look at it again. So here comes the reactant. The chiral center is here, and it basically repels it, and it costs a lot more energy for that reactant to get past that chiral center. All right. What happens when the substituent is much bigger? All right. Let's change that methyl group into a tert-butyl group. What happens when that's much bigger? Well, let's look at a video here and let's think about it. So here's the tert-butyl group, and it's in 3D. You can see the tert-butyl group is here. It is huge, right? And it's basically overshadowing that carbocation, which is the red carbon here. Let me turn this Jeopardy music down a little bit. All right. So here's my carbocation. I'm going to pause this right here. Notice the tert-butyl group here is basically like an umbrella over this. And so what's going to happen is the carbocation is going to be way more restricted if something tries to come in from this direction as opposed to coming in from this direction. So let's go back here. And if you look at what happens, so this direction or this approach is going to be blocked. This approach is going to be open, right? So what's going to happen when you increase the size of that substituent is the ratio between the stereoisomers in the product is going to be driven up even further. So maybe not 70-30, maybe this time with the tert-butyl it may be 90-10, or may even be 99-1. That I'm using random numbers here because I just want to make a point that with that pre-existing stereo center, it's going to change the ratio of the products. All right. So here's a question for you. What do you think is going to happen to the ratio between the two stereoisomers in the product when that chiral center is further away? All right. That's just something to think about for class on Wednesday. All right. So here's the take-home message. The proximity, how close or how far away, or the size, how large or small that pre-existing stereo center is going to dictate the outcome of the reaction. It's going to determine what the ratio is between the two stereoisomers. The further away the chiral center is from the reactive site, the less influence it has, and then the smaller it is, the less influence it has. All right, so if you have any questions, you can tweet, you can email, or you can drop by the office. I want you to watch this video, watch it multiple times if you need to, and ask questions, and we'll have an assignment when we come to class on Wednesday based off this video. All right, peace.